I'm trying to do this experiment with this balloon, but
Yeah?
I think I need more electrons.
Sure.
Do you mind if I borrow some from your hair?
My hair? David, I'm already having a bad hair day as it is today. You're just gonna make it worse. I know it.
Well, it was all for the cause of science, Dad.
What did you need them for?
This.
Oh, static electricity. Cool. Well, maybe we should tell them a little bit about static electricity. What do you think?
That's probably a good idea. Well, it all has to do with how atoms are arranged. In every atom, there are protons and neutrons in the center of the atom, the nucleus. And then there are electrons whizzing around the outside.
That's right. And so what happens, those electrons on the outside can actually be rubbed off of a substance. His hair, for example, let's use David's hair this time. When I rub his hair, I'm taking electrons from his hair and they're transferring through this friction to the balloon. So the balloon is getting a negative charge, his hair is getting a positive charge. Now, why does his hair stand up? That has to do with the law of electric charges.
Right. Which is that like charges repel,
And opposite charges attract. So static electricity is the buildup of a charge on an object. In this case, our balloon got a negative charge. David's hair got a positive charge. That's static electricity. Kristen here is going to help us explore static electricity. We're going to put her on top of the Van de Graaff generator, and then we'll turn it on, and we'll find out what happens when this gets charged and she gets charged. You ready? Here we go. See what's happening to her hair? The same thing that happened to my hair earlier. So she's also having a bad hair day too. Static electricity will do this to you every time. All right, here we've got Ollie the octopus. Ollie is going to do some demonstrations for us on the Van de Graaff generator. Okay, so when I turn this on, let's see what Ollie can do. Alright, pretty good, Ollie. Now, I've trained Ollie. Ollie can do a few things. For example, I can tell Ollie, down. Well, most of them obey. Or I can do something else. I can say, Ollie, grab my hand. And, it's got me. I'm stuck. Alright, so that's Ollie the octopus. Pretty cool. Down. Ollie can follow my instructions. Watch this. Ollie down. Ollie, let's do a fist bump. You shocked me again. So why does Ollie's hair stand up? It's for the same reason ours does when it's rubbed with a balloon. The generator is giving Ollie's hair a positive charge. All of them. All 8. Therefore, they repel each other, the law of electric charges. They want to get away from each other. The best they can do is stand up and separate. Why does Ollie collapse when I get close to him or when I touch him? The reason is because he's given his charge to me. I'm standing on the ground. So the charge passes through him to my hand and goes through my arm down to my feet and into the ground, and therefore he loses it and then has to build it back up again. Here's Ollie doing his dance, okay? Dance, Ollie, dance, dance. find out what happens when I put my hand on here. Shock. I have power, David. I have power. So I'm having to stand on an insulator. I'm standing on an ice chest right now. It's because I'm standing on this insulator, it's staying in me. I can even take my hand off of it and it stays that way until I step down. When I step down, the charge is going to leave my body and go into the ground. Watch this. There it goes. There we go. Fun, fun, fun. So how can David and I play catch with the generator? Well, it has to do with the law of electric charges. You're seeing it in action. At first, the ball is neutral. When the machine is turned on, opposite charges attract. The ball is attracted toward the positive dome. But when it touches the dome, it transfers its charge to the ball, so the ball becomes positive. Now they're both positive, and it's repelled away. When it touches David's hand, David takes that charge, and the ball becomes neutral again, which pulls it toward the dome, and on it goes. Okay, let's find out what happens if we put a nail on the Van de Graaff generator. So I have a nail sticking out here, and it's going to be a discharge point. So electricity, when it builds up here, the charge builds up. It wants to leave the ball, and it does so. It actually will create an electric field here around it. But if I give it a discharge point, it concentrates it right here. So when I turn it on, I put my hand here, I can actually feel air. I can feel coolness on my palm right now as the electrons are streaming away from this right here. The charge is, I can feel it. I think you'll be able to see it with a candle. Right now is being deflected away from that. When it gets close, that's the stream of electrons away from it. Pretty cool, huh? Hey, so we've had a lot of fun with the Van de Graaff generator. Now, why don't we find out how it works? So down here, we've got a motor. Motor spins this rod right here, and the rod is connected to a pulley. And this pulley down here is made of nylon, this plastic. And there's a belt going around it. And so when the motor is spinning, the pulley is spinning, and so is the belt, but it's creating friction. And that friction is causing electrons from the belt to leave the belt and go toward the pulley. And so the pulley is building up a negative charge with electrons. Now those electrons have to go someplace. Right below it, maybe about 1/8 of an inch below it, is a set of fine teeth made of metal, like a comb. And those teeth are grabbing electrons from the pulley, and then they're grounding them onto this metal base right here. Now let's take a look at the belt. This belt, as it's spinning, now it has a positive charge because it got rid of electrons because of the friction. So as the belt moves up here, it has a positive charge. And it gets to the top, and let's look inside here. And what we've got at the top here is another pulley. This one is made from metal. This is aluminum. So we have down here nylon. This was aluminum right here. So a different type of material. It doesn't grab any of the electrons from it like the bottom one did. Instead, what it does is it maintains that charge, the positive charge. And sitting right above it, inside this cup here, are some very fine teeth, just like at the bottom, and they're sitting like 1/8 of an inch above. And so when the charge builds up here, it's able to pass through the air and go to these teeth here. Now, our dome. Our dome sits on top of here and is connected to this whole thing. This dome, when electricity is not on, it's neutral. There's as many positive and negative charges in here, so it's neutral. When I turn this on, the belt becomes positive. Remember the law of electric charges, that opposite charges attract? Well, since this is positive, the belt's positive, all the electrons here that are negative want to jump onto the belt. And so they do. So if electrons are leaving here, this becomes positively charged now. And when this becomes positively charged, it spreads out over this whole thing. And when it spreads out, it begins to build up and build up and build up until finally it gets strong enough, the voltage gets strong enough to where it discharges. So if you've heard any of those snaps and those pops, that's this discharging into the air. Remember what we talked about? 1 inch of spark from this right here represents about 50,000 volts. Of electricity, 1 inch. And so that's how this works. Pretty cool, huh?
The greatest example of static electricity is lightning. Just as a Van de Graaff separates charges, that happens in clouds too because of friction. The wind and rain are mixing and causing friction, separating charges. And the area of a cloud builds up a negative charge or a positive charge, and it builds up until it finally discharges and strikes the ground. One lightning bolt can have up to 1 billion volts of electricity.
All right, so what do you think will happen if I put these aluminum pie plates on top of our Van de Graaff generator? Let's find out. All right, let's turn it on. Watch it go. As you can see now, my son eats a lot from Chipotle, so let's find out what happens when we have a bigger one. This guy's stuck here. Come on, go.